What's up, guys? This is Jahangir from MedPorium, and today we're going to be talking about everything redox. This includes what oxidation and reduction even is, how to assign your oxidation numbers so that you know which elements or which molecules are actually oxidizing or being reduced. We're also going to look at half reactions, as well as finding the oxidation half reaction and having our final formula. So let's talk about redox reactions, and I want to start by talking about oxidation versus reduction. So let's talk about oxidation, and I'm just gonna call it as code as blue. So oxidation is a loss in electrons, and the best way to memorize this is oil rig. So oxidation, and I'll put is loss in electrons. So in oxidation, we lose electrons. That's the oil part of oil rig. And for reduction, so reduction, we are going to see a gain in electrons. So reduction is, and I'll just put this as gain electrons. So that's the main difference between oxidation and reduction. And remember, you can use oil rig to memorize or to understand what those pretty much functions are. So with oxidation, we are losing electrons, and we're going to have more of a positive charge. With reduction, we're gaining electrons, so we're going to get a negative charge. Obviously, because electrons are negatively charged. So if we lose them, then we're going to have more protons and we're going to have a more positive charge. But with reduction, if we gain these electrons, which are negatively charged, then our molecule is just going to be negatively charged. So that's the main difference between oxidation and reduction. So I'm just going to scroll down and let's talk about oxidation numbers. So oxidation numbers, and I'm just going to use a symbol to denote our oxidation numbers. So let me make this a little bit bigger. So oxidation numbers, how to actually assign those for each molecule. Well, there's a couple rules that you need to know in order to actually assign these oxidation numbers. So one of the rules you have to understand is that elements will have an oxidation number of 0. So I'll just put oxy number of 0. So what are some examples of some elements that have an oxidation number of 0? Well, it's something like O2 or something like carbon in its basic state. So these oxidation numbers are going to be 0 because they are in their elemental form. So anytime you see O2 or Cl2 or maybe even H2, and you see one of the elements just by itself, maybe carbon is by itself, or for example, sulfur is by itself, then that is going to have an oxidation number of 0. Now, another rule you need to note is that monatomic ions, monatomic ions, and these are examples like iron or copper. So monatomic ions, and I'll just put, for example, like iron or copper. Whatever charge that monatomic ion is, that's their oxidation number. So for monatomic ions, and let me actually move these examples over here. Charge equals, and let's say oxy number. So for those monatomic ions, the charge of those ions equals their oxidation number. So for iron over here, that iron 2+, our oxidation number is going to be 2+. For the copper over here, 2+, our oxidation number is going to be +2. So that's how you know, and that's how you can determine those oxidation numbers for those monatomic ions, or those ions that mostly are going to be metals. All right, so what about some exceptions with some of the elements? Because some of the elements are going to have a, I guess you could say, superiority on their oxidation number, and they're always usually going to be constant. So what I mean by this is something like oxygen has a oxidation number of -2, usually. Now there's some exceptions like hydrogen peroxide, so I'll just write it over here, H2O2, where oxygen will actually have a -1 charge. Hydrogen over here will usually have a +1 charge if it's bonded to a non-metal, and it will have a -1 charge if it's bonded to a metal. So let me bring out the colors over here. And let's go with green for this example. So over here, we can see that oxygen is a -1 charge because hydrogen is bonded to a nonmetal and it's going to have a +1 charge. And 1 times 2 is going to be 2, so that's +2. 2 times -1 is -2, and that equals 0 because our overall charge over here is 0. And we'll actually go through some more practice problems or more of these questions where we're looking at a molecule and we're trying to find the oxidation number of some random element in there. So oxygen usually going to have a -2 charge, and hydrogen usually going to have a +1 or -1 charge. So next thing we need to talk about are halogens. So halogens. And halogens are going to be those group 7 elements such as fluorine. And this is going to exhibit a -1 charge. So fluorine is going to have, or -1 oxidation number. So fluorine is going to have a -1 oxidation number. And these are consistent with pretty much all the halogens. And same thing for those alkali metals, which are group 1. They're going to have a +1 oxidation number. And these include sodium and I don't know if you forgot some of them, but maybe even lithium. But those group 1 elements are going to have a +1. Group 7 is going to have a -1. And this is kind of similar to those valence electrons that they have, since group 1 has 1 valence electron and group 2, or group 7, my bad. So group 7 will have 7 valence electrons, and they only need 1 more electron to sort of take in order to be stable, in order to be complete. All right, so now here's the last thing to know, and this is one of, if not the most important thing to know for assigning your oxidation numbers, and it is the charge of molecules. So the charge of the molecules equals the sum of, and let me actually make this a little bit smaller so I can have more room. So the charge of the molecules equals the sum of the oxy numbers, or just oxidation numbers. So what do I mean by this? Well, let's look at something like CO2, for example, carbon dioxide, and I'll have different color code for oxygen. I'll just say oxygen is yellow. So oxygen, we know right off the bat, oxygen is usually going to be a -2 charge. So over here, we just have to put -2. 2 times 2 is 4, so -4, and our overall charge is 0. It's neutral. So this is going to equal 0, and we have X over here because we don't know the oxidation number for carbon. So all we really have to do is ask ourselves, what -4 equals 0? Or we can move this 4 over, and our X equals 0. So the oxidation number for carbon is going to equal 4 because 4 minus 4 equals 0, and that's +4. Now, what if we were looking at a molecule like HSO3 -1? Well, obviously we have this charge over here, which is going to be the sum of our oxidation numbers, and we know right off the bat, oxygen is going to be -2, hydrogen is going to be a +1. So if we write this equation, it's going to be 1, and let's do plus X, and let's make this yellow, minus, actually, let's do this, plus 3 minus 2 equals, and that's going to equal -1. Now the reason why I put a 3 over here is because we have 3 oxygens. So 3 times -2 is going to get us our total oxidation number for this O3. So if we do the math over here, this is going to be 6. So this is actually going to be -6. So let me actually change the color over here. So this is going to be -6 equals, and let's just copy paste this. This is going to equal -1. And we still have our 1 plus X over here. So all we have to do, we could either go through basic math and solve this, or we could just ask ourselves, 1 plus what minus 6 equals -1, and this should be quick math. So we obviously know 5 minus 6 equals -1, so our answer, X, is going to be 4, or let me actually change that color. So our oxidation number for sulfur is going to be 4. The reason why is because we have that oxidation number of 4, so 1 plus 4 is 5. 5 minus 6 equals -1, which is our overall charge of that molecule. So like we said, charge of molecules equals the sum of oxidation numbers. And this is important in finding oxidation numbers like sulfur, because we don't really know off the bat what that oxidation number is. But when we do know oxygen and we do know hydrogen, and we know the we know the charge of the molecules, and all we have to do is basic algebra to find that oxidation number. All right, so let's look at something like this, a chemical reaction, and it's asking us, or the question might ask us, which molecules are being oxidized, which ones are being reduced. Well, right off the bat, we want to assign our oxidation number. So for this example, yellow is going to represent oxygen. So I'll just color this over here. So yellow is going to be our oxygen, and let's say this Cr, I believe chromium is going to be green, and let's say our sulfur is red. So just color coding this so you guys know which oxidation numbers go to which molecule or which element. So now we can start assigning. So we already know right off the bat, oxygen is going to be -2. So we have -2 over there. But we have to keep in mind that this O7 is 7 times -2, which is -14. So we can write -14 over here, and that equals -2. Because this charge, like we said, the charge of the molecules equals the sum of our oxidation numbers. So we know that chromium is going to be our X. But we have 2 of chromium, so this is going to be 2X. So all we have to do is ask ourselves, well, what number times 2 minus 14 gets us -2? Or we can just do basic algebra. And when we do that, this is plus 14. So this is going to end up being 2x equals, and I actually forgot to put the 14 over here. So 14 minus 2 is going to be 12. So 12 divided by 2, what is that? Well, that's just going to be 6. So our X equals 6. The oxidation number for that chromium is going to be 6. So we can put +6 right there, just as a reminder that that is the oxidation number we assigned. And it's pretty simple. So we just used basic algebra, like we were looking back to our last page. We're just using basic algebra to find those oxidation numbers. So we got that out of the way as one of our reactants. Now let's look at this SO3 over here. So obviously our O3 is going to be -2. So this is just -6. So let me move this over here so I can have more space. And this is just going to be -6 equals, and let's see. This is going to equal -2, and our S is just going to be X. And since we only have 1 sulfur, we're just going to leave it as X. Over here we had 2 chromium, so we need to put 2X, but we're just going to leave this as X. And if we do basic algebra, this is +6. So -2 plus 6 is going to be 4. So let me change this. Our X is going to equal 4. And obviously, since 4 minus 6 equals -2. So our oxidation number over here for sulfur is going to be a +4. So now let's move over here, and right off the bat, we already know our oxidation number for this chromium over here, because if we remember one of our rules, the charge of a monatomic ion equals its oxidation number. So since it's pretty much that easy, all we have to do is just put +3 over here, just to remind us that that is the oxidation number. But now let's look at this SO4 -2. So right off the bat, we already know that oxygen is going to be a -2. So 2 times 4 is going to get us -8 equals, and let me change the color here, -2. The sulfur, remember it was red, so that's X. So X minus 8 equals -2. Well, you can just use quick algebra or just basic math. And this is just going to be 6. X equals 6. Because 6 minus 8 gets you -2. So our sulfur over here is going to be a +6. Alright, so now we got the hard part out of the way. We just assigned all the oxidation numbers. Now we need to ask ourselves, which one is oxidizing or which one is in oxidation? And let's see, which one is in reduction or being reduced? Reduction. So, if we remember from oil rig, oxidation is a loss of electrons. And if we lose electrons, then we're becoming more positive. So let's look at chromium for this instant. Chromium is going from +6 to +3. It's losing its positive value, so that's obviously not getting oxidized. Oxygen is just staying constant, just -2 throughout the whole, I guess you could say, reaction. So we don't have to worry about that. But look at the sulfur over here. So sulfur goes from a +4 to a +6. And if we know from oxidation, we're losing electrons. When we lose electrons, we have more protons and we gain a more positive charge. So with oxidation, we're becoming more positive. So this is why sulfur is the one being oxidized. So sulfur is the one being oxidized because it's going from a +4 to a +6, becoming more positive. Now with the reduction, as we can see from the chromium, we're going from +6 to +3. And if we remember oil rig, reduction is a gain in electrons. When we gain electrons, we become more negative. So we're kind of becoming more negative. We're going from a +6 to a +3. We're losing that positive value, and that's why this chromium, I'm just going to put Cr because I really don't know how to spell chromium. Now another question might ask you is, and I'll just copy paste this, what is the oxidation agent, or what is the oxidizing agent? So I'll just put agent, and in the flip side, what is the reduction agent, or what is the reducing agent? Just anything that has to do with agent, and agent is the one that causes it. So I usually kind of think of this as if you're the one being oxidized, you're the reduction agent. If you're the one being reduced, you're the oxidizing agent. And this is because it's flipped around. And a more conceptual way to understand this is with oxidation, we know that sulfur is being oxidized. So sulfur is losing an electron, but it is also helping with the reduction because it is losing an electron and it's contributing to reduction. It's contributing to a gain in electrons for another element. This is why sulfur is our reduction agent. And let me change the color over here. So sulfur is our reduction agent because this is the element that is causing reduction by losing its electron. Now, on the flip side, our oxidation agent is that chromium because it is the one that is taking the electron. So think of it like this. Chromium is helping sulfur lose its electron by taking it. So, and just like I said, easier way to remember this is if it's getting reduced, it's the oxidizing agent. If it's getting oxidized, it's a reduction agent. It's just flipped around so that it's better to understand. And this is actually pretty easy to understand once you know that it's just flipped around. So now I want to keep building off of this chemical equation, but now let's talk about half reactions. So half reactions. And half reactions really help us understand how each of these sort of elements are interacting with each other. So let's look at the reduction half. So for the reduction half of the reaction, we know that this chromium is going to be reduced. So all we have to do is just write down which of those molecules is that Cr binded to. So it's Cr2O7 with a -2 charge, and that goes to chromium 3 plus. And one thing I actually forgot is that we need to add our electrons. So the electrons that were added in order for this reaction to occur, and there are 6 electrons added in order to get to our Cr3 plus. Now you might be wondering, well, why 6 electrons? Well, if we look back to our oxidation numbers, and I'll actually write them again, we're going from a +6 to a +3. So if we didn't have 2 chromiums, then this would be a +3 electrons. But since we have 2 chromiums going from a +6 to a +3, so they're pretty much gaining electrons, we have 2 chromiums that are gaining 3 electrons each, and that's why we have a +6 for the electron side over here. Now, But one thing you might notice is that we have 7 oxygen over here, but 0 oxygen over on the product side. So with the reduction half, we need to be adding either hydrogen or water in order to balance this equation. So one thing we can do automatically is plus 7H2O. So that takes care of our 7 oxygens, but then we have 14 hydrogens over here. So all we have to do is just add those 14 hydrogens. So this is just going to be plus 14H plus, and that is our final reduction half reaction. As you can see, it's fully balanced because we added 14 of those hydrogens and 7 of those waters. Now, what about the oxidation half? So I'm going to scroll down over here and let's talk about the oxidation half. Oxidation half, or oxidation half reaction. So we know automatically that the sulfur was the one being oxidized. So our oxidation half sort of reaction is going to look like this. 7SO3 minus 2 goes to SO4 minus 2. And if we remember, we went from a plus 4 to a plus 6. So I'll just write this down just as memorization. So plus 4 to plus 6. So we're going from 4 to 6. So you might be wondering, well, where do we put those electrons? Which side do we put them on? Well, we put it on the product side. We put those 2 electrons on the product side because we're losing those electrons. We're still accounting that we have electrons. This is where, when we put in the product side, we're basically showing that those electrons still exist, but we put it on the product side because it's not part of the reactants. We lost those electrons, which is why we put it on the positive side. And now we have to account for this unbalance in oxygen. So all we have to do is just add enough water or hydrogen to balance this out. And it would look something like this. So we have 4 oxygens over here, 4 oxygens over here, and we have 2 hydrogens, 2 hydrogens. So this is fully balanced out. But remember that these are half reactions. And 0.5 plus 0.5 equals 1. So these half reactions need to add up in order for us to get that final reaction. So for that to occur, we need our electrons to be the same number. Over here we have 6 electrons, over here we have 2. So what we have to do is multiply by 3 in order to get to that 6 electron side. So once we do that, we end up with this sort of reaction. So we can just cancel out our electrons and pretty much add up everything. So what we're going to end up with is going to be Cr2O7, and forgot the minus 2 over here. So minus 2, and we're going to have a plus 3SO3 minus 2. Then we'll also have plus 8 hydrogens because 14 minus 6 is going to get us 8. And this is pretty much, as we remember from those net ionic equations, where when we have a same element on the product side and the reactant side and the product side, we subtract those out, and whichever one is the biggest on which side stays there. So we're gonna have that 8 hydrogen on the reactant side. And let's see, so all we have left now is we're moving to the product side. So we have 2 of the Cr3 plus, and over here 7 minus 3 is 4, so plus 4H2O and plus 3SO4 minus 2. So this is the reaction we end up with. Our half reactions have added up, and this is the final reaction that we end up with. So hopefully that helped you guys in any way of understanding redox reactions. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.